The design of an aerodrome departure procedure is in general dictated by the terrain surrounding it. It may, of course, also take into account other considerations, such as the proximity of other aerodromes, adjacent ATS routes, or restricted, prohibited and danger areas. All these factors in turn influence the type and sighting of the navigation aids required to provide track guidance for the departure route. From the point of view of aircraft operators, the use of in-cockpit systems, such as Automated Takeoff Thrust Control Systems, ATTCS, and noise abatement procedures, need to be taken into account as well. Where no suitable navigation aid is available that can provide specific departure track guidance, then the criteria for omnidirectional departure plates are defined. Wherever possible, a straight departure will be specified which is aligned with the runway. If, to avoid an obstacle, a turn of more than 15 degrees is required, a turning departure is constructed. Departure procedures will be established for each runway to be used, and will define the procedures to be used for each category of aeroplane based upon an all-engines running procedure design gradient, PDG, of 3.3%, to achieve minimum obstacle clearance. This procedure will assume that pilots will not compensate for wind effects if using radar-vectored departures, but will account for wind if on a departure route that is expressed as a track to be made good. Unless radar vectors are specified, pilots should assume they must take the wind into account to follow the track prescribed in the procedure. Consideration of obstacle clearance in planning departure procedures is of paramount importance, and unless otherwise stated, the procedure design gradient, PDG, is assumed to be 3.3%. The PDG is made up of 2.5% gradient of obstacle identification surfaces, or the most critical obstacle penetrating these surfaces, whichever is higher, and 0.8% increasing obstacle clearance. A 2.5% gradient equates to 152 feet vertically for every horizontal nautical mile. The more easily remembered figure is 200 feet per nautical mile for the 3.3% standard PDG. Published gradients will be specified to an altitude or height, after which the minimum gradient of 3.3% is considered to exist. The final PDG continues to exist until obstacle clearance is ensured for the next phase of flight, en route, holding or approach. This is when the departure procedure is defined to end. The minimum obstacle clearance equals 0 at the departure end of the runway, DER, and thereafter increases by 0.8% of the horizontal distance in the direction of flight, assuming maximum divergence of 15 degrees. If the resultant PDG is too steep, a turning procedure to avoid the obstacle laterally might be the answer. Alternatively, the aerodrome operating minima could be increased until the obstacle can be avoided visually. In the turn initiation area, the minimum obstacle clearance of 295 foot is provided. Of course, in specific areas of more mountainous terrain, increased obstacle clearance will be afforded. If DME is available, additional height or distance information is made available. Mountainous terrain is not defined, but when designing departure procedures, if average wind speeds of more than 20 knots prevail and the terrain produces downdrafts, then increased obstacle clearance criteria are applied. Aircraft category also plays a part in defining departure procedures, because the speed of the aircraft clearly influences the size and shape that departure procedure will be. The table you see here defines the maximum speeds for each category of aircraft that ensures safety within the published procedure. There are two basic types of departure routes, straight or turning. Departure routes are based on track guidance acquired within 10.8 nautical miles from the end of the runway, DER, on straight departures, and within 5.4 nautical miles after completion of turns on turning departures. That is, 20 kilometers for straight and 10 kilometers for turning departures. The design of the instrument departure routes is based on the definition of tracks to be followed, along which the pilot is expected to correct for known wind and remain within the protected airspace. A straight departure is one in which the initial departure track is within 15 degrees of the alignment of the runway. Track guidance may be provided by VOR, NDB or RNAV. At this point, we can usefully mention colour coding. The shaded areas are considered secondary for minimum obstruction clearance, whereas the clear areas along the departure track are considered primary. We will look at this in more depth later. If a departure requires a turn of more than 15 degrees, a turning area is constructed, and the turn required is to be commenced upon reaching a specified altitude or height at a fixed facility, like a VOR or NDB. Straight flight is assumed until reaching an altitude of at least 394 feet above the elevation of the DER. At least 90 meters of obstruction clearance must be guaranteed in the turning area. You should note, especially for examination purposes, that 30 meters is approximately 100 feet. This fact will allow you to make sense of many of these difficult heights. For example, before metrication, straight flight was assumed to 400 feet above DER, and a minimum of 300 feet of obstruction clearance was guaranteed in the turning area. In the event of in-flight emergencies, post V1, aircraft operators are required to provide contingencies that deal with safe operation of the aircraft during this phase of flight. An omnidirectional departure procedure is designed when no track guidance for departure is available. Departure criteria are developed using undefined omnidirectional initial departure tracks. In practical terms, this means that once off the end of the runway and at a safe height, aircraft may be navigated in any direction required to achieve the initial en route point. It may be that some sectors of this departure area may contain an obstacle that precludes departure in that direction, but this fact will be identified on the departure plates. The basic procedure determines that the aircraft will climb on the extended centerline to 394 feet before any turn can be specified, and at least 295 feet of obstacle clearance will be provided before turns greater than 15 degrees will be specified. If obstacles don't permit omnidirectional departure procedures to be designed, straight or turning departure procedures must be produced. Alternatively, it must be ensured that ceiling and visibility will permit obstacles to be avoided by visual means. At this point, we can usefully discuss minimum obstruction clearance, MOC, in terms of the departure footprint. Notice the two areas that extend from the departure end of the runway. These are the areas in which obstruction clearance must be guaranteed at the rate of 8 meters per kilometre. That is, 48 feet per nautical mile. But what defines the lateral extent of the MOC footprint? The footprint leaves the DER 75 meters either side of the extended centerline and splays away at 15 degrees. That is, if you recall, because track adjustments to 15 degrees are allowed. The length of Area 1 will usually be 3.5 kilometers. That is, where a PDG of 3.3% would reach a height of 120 meters above the departure end of the runway. If, because of an obstacle, the procedures required an increased PDG, then of course the aircraft would reach 120 meters above DER before 3.5 kilometers. Area 2 allows a further track adjustment of 15 degrees, and its length will depend upon the minimum height above DER that must be reached before the aircraft can turn in any direction and not have to worry about obstacles. If the aircraft is able to turn onto any heading at a height of 120 meters above DER, then the length of Area 2 will be 0. However, because of an obstacle, should that not be high enough, then Area 2 will increase until the aircraft does reach a height at which it can be turned onto any heading and safely clear that obstacle. Because there is no navigation aid providing track guidance, the whole of Areas 1 and 2 are considered primary. That is, the required obstruction clearance must be provided within the entire footprint. When track guidance is provided, then the footprint can be divided into primary and secondary areas. Recall that the secondary areas are in brown and bound the clear primary areas. Here is a vertical cross-section. You can see that, in the primary areas of the footprint, the full obstruction clearance must be guaranteed. However, MOC reduces to 0 as we move away from the primary areas through the secondary areas. If there is a particularly troublesome obstacle, then of course the departure track can be adjusted until the obstacle is overflown by a secondary area at a height that clears it sufficiently. This ends our discussion on minimum obstacle clearance during departure procedures. Departure procedures, departure routes and standard instrument departure charts are published in accordance with standards contained in Annex 11 and Annex 4 to the Chicago Convention. Here you can see a typical plate for a standard instrument departure, more commonly known as a SID plate. Don't forget, all standard instrument departures, or SIDs, start at the departure end of the runway and end at the point of joining the ATS route system. Normally, an aircraft with a full IFR flight instrument panel will be required to utilize all the facilities and comply with the requirements of the SID. At the end of a SID, you will be well placed to continue en route in the airway or under radar control. FMS or RNAV equipment may also be used when flying defined departure procedures, providing the procedure is monitored using the basic display normally used with that procedure, and the tolerances for flight using raw data on the display are complied with. GNSS procedures allow for SIDs to be downloaded into their databases and a fully automated departure completed. As in the case of the FMS or RNAV procedure, the pilot is required to monitor the procedure with reference to the direct input data from other nav aids, such as VOR, NDB, or DME. The aim is to eventually replace VOR or DME with GNSS. These procedures will use Precision RNAV, known as PRNAV, which may be augmented by altimetry cross-reference, Baro VNAV, to give the precision element to both arrival